I gotta get it back.
Could you put the phone off? But Deborah's phone. Hello and welcome to the next session in this Digital Futures Doctoral Consortium series on artificial general intelligence. The Digital Futures is an educational platform that we've set up to democratize education. Our view is that education should be a human right and not a privilege of the wealthy, and we are therefore live streaming this all around the world, and we're recording it for everyone to watch for free. And the Doctoral Consortium is a particular initiative within the Digital Futures platform, where we are trying to offer a platform for doctoral students all over the world where they can come together rather than studying in small groups. And this particular series is one where we're looking at the challenge of AGI, and especially in the context of neuroscience and other related disciplines. This is a very special week for the world of AI. Many of you will know that in the past few days, both Geoffrey Hinton and also Demis Hassabis have been awarded Nobel Prizes. Coincidentally, both are British, and both are AI scientists interested in neuroscience. In fact, Demis Hassabis has a PhD in neuroscience, and both of them studied from Cambridge. Of course, there is a long history of individuals such as this. In fact, Alan Turing himself was somebody deeply interested in neuroscience, also studied in Cambridge. Anil Seth, who's been on here a couple of times, also studied in Cambridge. And today's guest, Karl Friston, was also there. He's currently a professor at UCL in London. Karl is a very, very distinguished neuroscientist, probably the top neuroscientist in the UK, and one of the most cited scientists in the world. He's also connected to the world of AI and is the chief scientist for Versus AI, a California-based cognitive computing company specializing in biologically inspired distributed intelligence. Karl is an authority on brain imaging and theoretical neuroscience, and is especially famous for his work on the free energy principle and active inference. Both of these are now being advanced as potentially leading to AGI. Karl, it's wonderful to have you here. Welcome.
Well, thank you very much for having me. It's a great pleasure to be able to talk to you. And just to send my congratulations to Jeff and Demis, who also, all three of us, used to work at UCL, literally in the same building, or at least next door to each other. I'm going to give my favorite lecture, and it's about the free energy principle. It's really looking at intelligence through the lens of neuroscience, but naturalized in terms of physics. So this is very much a sort of first principle account of the way in which we make sense of the world and make decisions about how to sample data from that world in the next moment or in the future. I am going to give a formal presentation. However, I imagine that the panel would want to have some discussion and questions at the end. So if I talk too much, please interrupt me, and I'll just show you what I would have shown you had we had enough time. So I'm just going to keep on talking until I'm interrupted, and then we can get into the sort of more interesting issues about the implications of this biomimetic or natural approach to intelligence as what are the basic principles that underwrite natural intelligence. So,
Karl, please feel free to go on as long as you want. We're very flexible here.
Right. Well, that's very nice to hear, but I often find the best stuff actually happens in exchange at the end. So if we can make the end as long as possible, I think that will be that will be appreciated by the audience. But let me briefly go through the fundaments of the free energy principle as it applies to intelligent behavior or sentient behavior, something we often refer to as active inference. And I'm actually going to let Jeff do the heavy lifting. So I found this actually just a few weeks ago, and Jeff was being asked if you could go back in time and meet one of your heroes, who would you choose? And this was his answer.
I think you might have pressed the start button bottom left.
Can you hear this, or is this only audible to me?
Oh, no, we can't hear it. Oh, I think what we need to do is unshare and then share again and put the sound on. My apologies, we should have checked that.
Oh, well, no, don't worry. I'll just paraphrase what he was saying. Everybody was expecting him to say something like Turing, and his choice was exactly my choice, which was Helmholtz. And the rationale he gave for wanting to speak to Helmholtz was because of Helmholtz's bilateral contributions, first of all, in terms of physics and specifically Helmholtz in free energy, but also because of his contributions to perception and sense making in the form of unconscious inference. So it summarized exactly the conjoining of physics and physiology in the service of understanding intelligence and sense making of the sort that I wanted to talk about. So my talk is going to be sort of half physics and then half neuroscience. So we're going to start off by talking about the statistics of life, with a special focus on something called Markov Blankets and the Bayesian mechanics that ensue from Markov Blankets. And to cut a long story short, Markov Blankets are going to play the role of defining something that you want to talk about that may or may not show some kind of intelligent behavior. I'm then going to tell exactly the same story from as if I was talking to psychology students or neurobiology students or medics, discussing the anatomy of inference in the brain with a focus on predictive coding and neuronal networks. However, it is the same story as the physicist's story covered in the first half of the talk. And if we have time, I want to conclude just by thinking specifically about the inactive aspects of intelligent behavior, namely what it is to be an agent and what that would entail in terms of the statistics of life or biotic self-organization and the requisite architectures, computational architectures, computer science architectures that you would need to bring to the table to model, reproduce, or simulate agency. So I'm going to start with another physicist, specifically Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? So this question posed by Schrödinger, I think, is a great question. We're not going to answer this question completely, but we are going to pick up on the notion of a spatial boundary and just ask, can you ever talk about anything in the absence of being able to individuate or separate that thing from everything else? And if not, how are you going to define the boundary or the mechanism or the calculus that allows you to individuate the thing of interest, the system of interest? I'm going to use as that construct the Markov blanket as a statistical boundary. For those of you who don't know what a Markov blanket is, I've tried to illustrate that with this little schematic. So imagine a universe where the states, some arbitrary states of different parts of this universe are denoted by these cyan circles. And the influence of one state on another state is given by an edge or an arrow here. And with this, I can now identify some internal states, say my states. And if I've done that, in virtue of the dependencies or the influences among the different states, I can now identify the Markov blanket. And the Markov blanket is just a collection of states that comprise the parents, the children, and the parents of the children. And the role that this Markov blanket or boundary plays is that if I needed to know how my states were going to evolve over time, given the rest of the universe, I would only need to know my boundary states or my Markov blanket states. Technically, what this means is that my dynamics are conditionally independent of all the rest of the states in the universe, conditioned upon or given my blanket states. Now I'm going to make a further move here. I'm going to divide the blanket states into sensory states and active states on a very simple rule, namely the sensory states influence but are not influenced by the internal states, and similarly the internal states influence but are not influenced by the active states. And with that rule, I've got, if you like, a way of partitioning states, some very abstract states of any universe, into the states that constitutes a thing, a person, a particle, a population. We'll call those particular states. And those particular states subdivide into the internal states, say my internal states, and my blanket states, active and sensory states. So you may be asking, well, what would that look like? Well, let's just take me or a brain. In this partition, we can consider all the internal states of my brain, for example, neural activity and connection strengths, connection weights, as constituting everything that I would need to know in terms of listing the internal state of my brain. And then these internal state influence my actuators, my active states, my autonomic reflexes that influence the external states in the universe, that reciprocate by returning sensory states on my sensory epithelia that then update or influence my internal states. So what we have now is a mathematical image of effectively a perception action cycle where the outside influences the inside through sensory states, that will be, say, perception, and the inside influences the outside through active states, and we can read that as a kind of action. So with that in place, what I want you to do now is, for a moment, forget about the Markov blanket. We're just going to do a bit of 101 physics. And then what we're going to do is to put the Markov blanket back into play and ask what special kinds of mechanics arise from the simple existence of a Markov blanket, or more simply, the simple existence of a way of separating something from everything else. And the physics that I want to start with is the foundation of all of physics, ranging from quantum physics through statistical mechanics through to classical mechanics. And it all starts with this random differential equation or dynamics, for example, a Langevin equation, where the rate of change of something, some states, is a lawful function of where you are in this abstract state space, plus some random fluctuations. And I've cartooned that here in terms of two states on the X and the Y axis here, so that we can imagine as time unfolds, I'm in this state, and then I move along this trajectory here into another state and another state. And this can be at any scale. It can be at any space or time scale. So for example, it could be some very, very fast oscillation of an electrochemical sort in one of my brain cells. It could be my cardiac cycle as it unfolds during beat to beat. It could be me walking. It could be me getting up in the morning, doing my emails, having a cup of coffee. It could be over the year. The key thing here is that if I exist and I can maintain my boundary, my Markov blanket, I will always have characteristic states that I keep returning to, or at least the neighborhood of those states, so that you would recognize me as characteristic of me, the kind of thing that I am. Technically, that's called a pullback attractor. And that affords an interesting interpretation of this trajectory, this itinerant dynamics of things that exist in the sense of being separable from their environment. We can interpret this as a probability that you'll find me in one of these states, these set of attracting states, if you sampled me at any random point in time. And that means, well, that's an important move because we know a lot about how this probability density itself changes over time. That can be written down in many, many different ways. I've written it here in terms of something called the Fokker-Planck equation. You could also interpret this as a time-independent Schrödinger wave equation. It's sometimes called a master equation when written in discrete time. The point here is it's a universal and really important description of physics, not of the state of things, but the probability distribution over the states that something could occupy. This is really useful because I've just said that things that exist in characteristic states are always attracted to this manifold or attracting set, which means that this probability distribution doesn't change in time for as long as I live, which means that the rate of change of this probability distribution is 0, which means that I can now solve this equation in quite a remarkable way. And that remarkable way is the first celebration of or nod to Helmholtz. I'm going to use the Helmholtz decomposition to express the solution of this as an equation which links the amplitude of the random fluctuations, the noisiness or the temperature of this universe, to the logarithm of the probability gradients that define this probability distribution. And effectively what that means is that I can express the dynamics, my flow, my neuronal dynamics, for example, in terms of the amplitude of the random fluctuations with a solenoidal component and the gradients of this probability distribution. And that separation into the what's called the dissipative and conservative part is due to Helmholtz, the Helmholtz decomposition. Just to make that a little bit more intuitive, what we're basically saying is that for any system that has some invariance over time and possesses a Markov boundary, we can always write down, or there exists a description of that system in terms of flow, which is dissipative, down probability potential gradients or up probability gradients, so that the system is gathering itself together, resisting the dispersive effect of these random fluctuations. And at the same time, there's a dynamics or a flow that is at right angles to this gradient flow, this dissipative flow, and that's called conservative flow. And I repeat, that's due to the Helmholtz decomposition. Applied here in the context of, say, hydrodynamics, we'll all be familiar with this, with the water flowing down the tub hole, the bath hole, and at the same time circulating around without changing its level in a conservative fashion. So that's elementary physics of everything. What about the Markov blanket? Well, that law, that fundamental gradient flow due to the Helmholtz decomposition, applies not only to all the states, but all the partitions that we talked about when thinking about individuating something from everything else. So we can also write down the Helmholtz decomposition, or this gradient flow here, for the internal states and the active states. And the notion I'm pursuing is that this basically describes perception and action in the following sense. Both perception, both the internal states, say my neuronal states, and what I do, how I move, are both can be described as trying to do an uphill or gradient ascent on this quantity here. And it's the same quantity, and it's not a quantity that depends upon the external state. So it just depends upon the sensory sector of my Markov blanket. So how could we interpret this quantity? Well, I've just said that the states, the probability distribution determines the attracting states, or the states that are characteristic of me, basically those kinds of states that are characteristic of my self-organization, the states that I aspire to, that have value for me, that determine the kind of thing that I am, which means that both perception and action, or the dynamics on internal and active states, look as if they're trying to maximize those states, the probability of attaining those states that have value for me. And of course, this is captured beautifully in things like reinforcement learning, if you're an engineer, optimal control theory, if you're an economist, expected utility theory. If you're an information theorist, you would read this quantity in a very different way. You'd put a minus sign in front, and you'd call this self-information. Some people call it surprisal, or more simply surprise, which means that we can also read perception and action as looking as if they are constantly trying to minimize surprise or self-information. And we'll see later that this free energy, this variational free energy, is a bound on this surprise. And from this, we can now read off the principle of maximum mutual information, or the Infomax principle, or equivalently the minimum redundancy principles of people like Horace Barlow, another great Cambridge theoretician, and indeed the free energy principle itself. That's good, because the average of surprise or self-information over time is known as entropy, which means that action and perception is in the service of minimizing entropy, or it looks as if it is trying to resist an entropic dispersion. And of course, that's the holy grail of self-organization of the kind, for example, introduced by Hermann Haken in the form of synergetics. But if I was a physiologist, it would simply be a statement of homeostasis. It's just a statement that things that persist and maintain their boundaries will look as if they possess a generalized homeostasis. They will keep the essential variables within bounds, resisting the dispersion due to random fluctuations. There's a final interpretation that I'm going to leverage, which is a statistical one. So if a statistician saw this equation, what she would say is, well, it looks as if perception and action are trying to maximize the probability of some sensory data given a model of those data. So I'm no longer me, I am a model of the causes of my sensory data. And this Bayesian model evidence maximizing interpretation is exactly equivalent to things like the Bayesian brain hypothesis. You may read about evidence accumulation in many contexts, and predictive coding is one particular aspect or description of this fundamental process, both in engineering and over the past few decades in neurobiology and the neurosciences. And I'm going to sort of illustrate that, that perspective in the second half of the talk. So let's move on to the anatomy of inference predictive coding neural networks. I'm going to say basically exactly what I've just told you, but using a very different language and a different set of heuristics or perspectives on understanding the teleology, or the, if you like, describing this emergent kind of dynamics in terms of things that we would understand as a psychologist, or indeed throughout the life sciences. The story could start with Plato. I've chosen to start it here in the 16th century with this oil painter, famed for painting still lives, that when viewed from a different perspective, give you a very different visual impression. So if before you saw a bowl of fruit and now you see a face, the point he's making here is that you made that face. Your brain constructed an explanation, a hypothesis, a fantasy, an hallucination, an illusion that was apt to explain the sensory impressions on your eyes, your sensory epithelia, your retina. The idea here, as Andy Clark would say, that perception is not a passive inside-out process where you're ingesting data and trying to make sense of it. It's very much an outside, an inside-out process where you're actively constructing explanations and hypotheses and then putting those hypotheses, those fantasies to the test by comparing what you would predict against what you're actually sensing. And I use the word fantasy here because that licenses the notion of things like the brain as fantastic organs, organs of a statistical sort, organs of prediction. This perspective, I think, was probably most compellingly and beautifully articulated by Helmholtz in the form of unconscious inference. For example, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. So again, what it's saying is the face has to be on the inside in order for you to perceive it as an explanation for the sensory evidence that you're sampling, in this instance, with your eyes. And clearly that idea is very close to ideas of people like Richard Gregory that can be read equating perception with hypothesis testing. These ideas have been taken up to great effect in machine learning by Geoffrey Hinton and his colleagues such as Peter Dayan. And indeed, they built a Helmholtz machine as a metaphor for the Bayesian brain. And they borrowed from Bayesian probability theory, and in particular, the work of Richard Feynman on variational approaches to evidence accumulation and solving difficult pathological problems in his quantum electrodynamics. And that's where the free energy of an originally Helmholtzian sorts comes from. So the variational free energy is Feynman's version of Helmholtz's free energy. Let's go back to Helmholtz. Always imagined as being present in order to produce the same impression on the nervous mechanism. So how can we read this impression on the nervous system in terms of this physics account of self-organization based upon Markov blankets? Well, the sensory part of the Markov blanket can now be regarded as a sensory epithelium or veil or curtain that is separating me from the outside world. And the sensory impressions are effectively the shadows cast upon this sensory veil by the external causes. And if I now take this Bayesian reading, this statistical reading of the fundamental gradient flow, the Helmholtz decomposition, then what that means is I can interpret that as that I am compelled, or I can be described as trying to identify the causes of these sensory impressions. So how does that work in the brain, for example? Well, we know how it works because it must be described in terms of this Helmholtz decomposition here. What I've done here is just express this for the internal states, and I've replaced the log of the probability of the sensory states with this free energy expression, which is usually in physics the negative of the log probability. And what I've done further is just to read now the internal states as parameterizing some belief that I have about the external states, about the causes out there that I can never see directly. I can only see their consequences on my sensory input. And I'm taking my internal states as representing or standing in for these probabilistic or Bayesian beliefs, in this instance with a Gaussian distribution. And if I make this normal or Gaussian distribution assumption, sometimes called the Laplace assumption, I can rewrite this Helmholtz decomposition in terms of something that if you were an engineer, you'd recognize immediately as a Kalman or Bayesian filter. So how does that happen? Well, the conservative part can now be read as a gradient flow on something called a prediction error, while the solenoidal, the dissipative part, while the conservative part or the solenoidal part is effectively a prediction. So heuristically, what that means is that my best guess, my expectation, the mean, the average, or the expectation of some state of the external world can be predicted based upon what I think the world is like now, and then I just update it with this differential operator here. And then I can update that based upon the prediction error. So what's a prediction error? Well, we can see from this equation it's just a free energy gradient, but more intuitively, we can understand it in terms of the following schematic. Imagine I had this sensory impression on my Markov blanket or my retina, and I had some expectation that it was caused by some external or hidden state that is hidden behind the Markov blanket by a howling dog. And if I had a generative model that would generate what I would see or sense if it was caused by a howling dog, I can compare my prediction of what I would see with what I'm actually sensing, and the prediction error is just the difference between them. It's just the mismatch between my sensory samples or sensory data or my input data or my content and predictions of that content under some expectation about how it was generated. And all that this equation is saying, which is just the Helmholtz decomposition, is that this prediction error is then used to drive the expectations, say my neuronal dynamics, until the free energy is minimized and the prediction error goes away. At which point, of course, my predictions should be perfect, and I've minimized my prediction error and I've minimized my free energy. Note I will never know what actually caused my sensations. In this instance, it was actually a cat, not a dog. I'll never know that, but that doesn't matter. If I can keep my prediction errors minimized for the amount of time that I have lived, then job done. That is sufficient to comply with the rule or the principle that I'm going to be minimizing my my free energy. Technically, the path integral, so it is a principle of least action. But this is the neurobiology part of the story, so forget about least action. Think of it in terms of prediction errors, and that means we can forget about all the physics and just reduce the imperatives for active sensing, for an active engagement with our sensorium in terms of minimizing prediction error. So how can we minimize prediction error? Well, there are two ways. I can either literally change my mind through some neuronal dynamics such that the predictions become closer to the sensations, and we can read that as perception, or I can act upon the world to sample some new sensations that are closer to the predictions, and we can read that as action. So again, we have this theme that action and perception are in the service of minimizing the same thing, here, prediction error. Which means that action now can be read as effectively just fulfilling predictions of what I expect to happen. While perception is in the game of providing those predictions, but crucially, the circular causality implicit in this perception-action cycle means that perception depends upon action, because action provides the data or the content upon which you're basing your inference, your Bayesian inference, or your perception or evidence accumulation. So here's, if you like, a schematic that describes this process in neuroscientific terms. Remember before, in order to produce a prediction error, we have to have a generative model that will generate predictions given I have some expectation about what caused my sensations. In general, these generative models are deep models, they're hierarchical, they have a hierarchical depth as illustrated in this cartoon here. So let me just talk you through how this Helmholtz decomposition works, or predictive coding works, or Kalman filtering works, or evidence accumulation works. They're all names for the same basic thing that inherits from the background story, the physics story. So let's just take, say, visual input from the retina. And it comes in and it enters subcortical structures in the brain called the lateral geniculate bodies or nuclei. And these populations, these nerve cells here, are in receipt of top-down predictions from parts of the brain concerned with visual representations or expectations. And the top-down predictions are then matched with the bottom-up sensory information to form a prediction error. And then this prediction error, in accord with our Helmholtz decomposition, is then used to drive or change the activity in the visual cortex until the prediction error eliminates itself or resolves itself through this recurrent message passing. But notice in these deep models, these expectations now are themselves being predicted by second order representations or expectations, generating second order prediction errors that are used to refine and finesse and improve the representation at multiple levels of abstraction by minimizing prediction error at each and every level of the hierarchy. And you can have a very deep model should you want to. Let me now turn to action, though, and I'll just illustrate how action gets into this scheme by appealing to a different kind of sensory input, and that's in my world, or certainly in neurobiology, this would be called proprioceptive input. And this input is special because it reports the state of my action mechanisms, my motor or muscle plant, everything that can change, that I have influence over, that I can change. Proprioceptive input is a sensory input that reports the consequences of my active states. So we have this proprioceptive input from the eye muscles. It will enter the brainstem around the pons, and I could have predictions about where I feel my eye is pointing, for example, and that would engender a prediction error. And I can use that prediction error to update my beliefs about the state of my eye muscles, my oculomotor system. However, there's a much simpler way in which I can reduce this prediction error, not by changing my mind, but by sending the prediction error back out to drive the muscles until the muscles actually report what I have actually predicted. So what I've described here is in motor theory in biology, just a reflex arc. It's effectively reflexively in a closed loop way fulfilling top-down predictions or set points, where these set points are provided by all this deep hierarchical processing, providing a prediction of what I should be feeling with my organs of action, or which could be either muscles or there could be secretory organs. So that's the basic setup from the point of view of, well, a simple example in active vision. You could also think about this as effectively, as did David Mumford, predictive coding with reflexes, where there's basically convert a predictive coding data assimilation or evidence accumulation scheme or Bayesian filtering scheme into something that is active just by equipping it with the predictions of the consequences of action. So I'm going to close now by asking the question, is that sufficient to simulate and explain complicated biotic behavior of the kind that we study in psychophysics and psychology and the neurosciences? Well, yes and no. Yes, we can certainly produce very biomimetic kinds of behavior by just applying this Helmholtz decomposition and interpreting it in terms of predictive coding or active sensing, active inference. And this is one of my favorite examples. What we've done here is create a little synthetic agent and equipped the agent with some generative model that has autonomous dynamics, in fact, based upon a Lotka-Volterra system. And what the agent thinks the world is like is that there is some abstract attracting set that is wandering around, and that this controls the position of a visible point in extrapersonal space. Furthermore, there's a spring, an invisible spring attached to this invisible point that pulls the agent's finger around. So from the agent's point of view, the agent is predicting to both see and feel proprioceptively its finger being moved around. So when we realize and integrate those differential equations and simulate self-organization using that Helmholtz decomposition, what we see is movement that looks very reminiscent of biological handwriting. And furthermore, what we can do is we can now play with the various mixtures of input that underwrite this kind of active sensing or active inference. What we've done here, in fact, is to remove the proprioceptive input but replay the visual input so that the agent can't feel itself moving anymore, but still sees a finger writing. So from the agent's point of view, it's as if some other agent is doing the writing. But the agent's got a perfectly apt generative model to predict the consequences of that action, can use exactly the same, if you like, neuronal representations to represent events in the sensorium in exactly the same way as if the agent was causing them. And this, in neurobiology, is referred to as a mirror neuron-like representation, namely using the same machinery to generate predictions of self-generated movement and the same movements that are generated by somebody else. And we've illustrated that here just by measuring the activity of one of these internal states, encoding this abstract dynamic, this central pattern generator, if you like, and plotting the activity when the activity is high above this threshold as a function of where the finger is in space. And what we see is sort of characteristic place field-like responses that are specific to certain locations in this space, with also characteristic direction selectivity, and crucially, the same kind of specificity when we're just observing or when with simulated observation as opposed to action. It takes a little bit longer for the inference scheme or the recognition to catch up, but once it realizes what's going on, then we get exactly the same kind of response profiles. So that's all very nice, but is this a good description of how we move? I would say probably not. There is no sense here of thinking about or planning what I'm going to do or any long-term consequences of my actions. So that begs the question, well, are there different kinds of systems and different kinds of Markov blankets, some of which, a small number of which, may actually evince a more intelligent kind of action and authentic agency? And I would submit there is, and it rests upon a very, very simple manipulation. Let's go back to our Markov blanket where we've got our brain here. And let's imagine we've got a very big brain, and it's sufficiently big and has sufficient hierarchical depth that the internal states do not have access to the actual action or active states. So I'm just going to remove that particular influence. And that has a really interesting consequence. And the consequence is effectively that now the action now becomes a hidden cause of my sensations. So it will look as if this kind of deep, large brain will be representing or inferring its own action. And this has the look and feel of something called planning as inference, or active inference of this now nuanced sort. And I've tried to cartoon the difference here in terms of, say, a single cell organism where the active states, so the active filaments of a single cellular organism, actually communicate directly to the internal states, as compared to, say, a mouse or me, where the active states no longer influence the internal states. And what that means is I can now describe the behavior of this kind of system or this kind of Markov blanket as if it was actually inferring its own action. And that inference, as before, for the actual active states is just a minimization of proprioceptive prediction error or a gradient flow on variational free energy. But now I have to introduce a new quantity, which is effectively the free energy I would see if I committed to a particular action. And we refer to that as the expected free energy. And I'll just finish now just by quickly overviewing a more, if you like, expressive variational account of behavior and agency in the context of intelligent behavior and indeed artificial intelligent behavior. Just by reference to the functional form of these two universal objective functions. So here's a free energy that underwrites this merely reflexive kind of predictive coding and sense making. And here's the expected free energy that is introduced when we think about agency as planning into the future and choosing those actions or policies or narratives, interventions that will result in a minimum free energy in the future. So this is a function now of the action, and if I can minimize this, then I can choose the action that is most likely to reduce my free energy in the future. Here are the functional forms. We haven't actually seen these before, but I think they're usefully written out. If you don't do maths, don't worry. I'm just using these in an iconic way to just to bring an intuition to the table as to how you can interpret the minimization of prediction error or maximization of model evidence and its variational bound free energy, often known as an evidence bound in machine learning, or ELBO. So if I wanted to write this down fully, this is what it would look like. And if I was a statistician, I would write it down like this. I would write it in terms of complexity and accuracy. So minimizing free energy is effectively trying to provide an accurate account of sensory input that is as simple as possible in accord with James's maximum entry principle and Occam's principles. What do I mean by complexity? Well, complexity just scores the degree I have to change my mind in accounting or providing an accurate account of these sensory data or this sensory content. And that's scored by something called a KL divergence between, or a difference, a statistical measure of difference between my prior beliefs before about the external states, before seeing the sensations or the content, and afterwards, where this is an approximate posterior, it's parameterized by my internal states. And I can just rearrange these terms to express the free energy in a way that somebody in machine learning would understand it. For example, if you were building a variational autoencoder in machine learning, then you would understand this free energy as a bound, a KL divergence, in this instance between the approximate and the true posterior, noting that this can be never less than zero. You can't have a difference that is negative. So this is a bound on the log of the evidence, the Bayesian model evidence, and that's why it's called an evidence bound. But the interesting thing is now, if I now think about this kind of quantity in the future, what do I have to do to make to understand this structure in the future? Well, the key thing about the future is that my sensations have not yet occurred. So they are now random variables, which means I now have to take my expected free energy now has to be an average over all the future observations I could obtain if I committed to this action. However, the functional form is very, very similar, other than the fact I'm now taking an average, an expectation under all the sensations that could ensue. And what happens is the complexity and accuracy become risk and ambiguity respectively. The divergence and log evidence become intrinsic and extrinsic value. So what are intrinsic and extrinsic values? Well, let's just unpack what these terms mean and link them to things that you may actually have come across in different fields. let's, for example, ignore the evidence. Let's assume that in the future, every sensation is equally probable. I don't care what happens. There's no extrinsic value. I'm just left with this. So what is this? Well, it's another KL divergence, Kullback-Leibler divergence, that basically measures the difference in my probabilistic or Bayesian beliefs about the external states with and without the sensory evidence. So it scores the information gain. It scores what some people refer to as Bayesian surprise in the visual search literature. It scores also the mutual information between the sensory consequences of the hidden causes that I am trying to reveal in terms of minimizing my expected surprise or my uncertainty. So put simply, the intrinsic value is the degree to which information gain reduces my uncertainty about the causes of my sensations. It underwrites curiosity, it underwrites exploration, it underwrites epistemic foraging, choosing those behaviors that are going to disclose observations that are going to reduce my uncertainty about how those observations were caused. Let me make things a bit simpler by removing a certain kind of uncertainty from the table. And the uncertainty I'm going to remove is ambiguity, where basically what I'm going to do is pretend that every external state of the world produces one definitive sensory input. So I can basically see states of the world. I still don't know what will happen to states of the world under particular actions, but there's no ambiguity about the external states causing my sensations. I'm just left with risk. What is risk? It's just another KL divergence. It's just the difference between what will happen if I commit to this action relative to what a priori I prefer or expect to happen. So the risk, again, is being minimized in the sense of complexity, but now it's in the future. So it's basically, I'm going to choose those actions that bring about expected consequences that are as close to possible as my preferred prior beliefs about the characteristic states that I should be in. I'm going to make a final move, and that's to remove all uncertainty now. So there's no intrinsic uncertainty and there's no risk. Now I'm just left with extrinsic value. And what's this? Well, this is where we started. It's just those states that are attracted to me, that have high utility for me. So I can read this as the expected utility and expected utility theory. So notice we've come back to sort of very classical reading of what good behavior by removing uncertainty from the problem. I'll close now just by giving you a numerical example of this kind of behavior with a special focus on this intrinsic value that you can also read as salience. You know, the salience of looking over there as scored by how much uncertainty would I resolve if I looked over there as opposed to looking over here. Excuse me. And we can simulate and quantify that. So, for example, if I was looking at this picture here, and I could only see a small foveal representation, how much uncertainty would I reduce my if I looked here as opposed to here as opposed to here? And we can plot this out, and what we get is this kind of salience map expressed in terms of negative expected free energy, which does seem to attract where people actually look when exposed to this image. And we can simulate this. This is a very simple simulation where the universe, from the point of view of this agent, can just be in three different states. She can be looking at an upright face, a sideways face, or an inverted space, but can only see a small fraction of the image and has to choose very carefully where to look next. And using this expected free energy, or this intrinsic value part of the expected free energy, she can choose those most informative parts of the image to look at, or in this instance, parts of the face to look at. And as she does so, she resolves her uncertainty. The salience map changes, and her uncertainty about what is the state of the universe, what is causing her sensory input, shrinks with successive eye movements until she reaches a right posterior conclusion that indeed it is an upright face. And with that final example, I'll close with reference to Helmholtz, another wonderful quote here. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed. I'll stop sharing now.
Well, thank you. What a terrific lecture. Very, very dense, but extremely sensitive and full of nuances. And I think a beautiful gloss to some of the sessions we had before with Andy Clark. Andy Clark appeared twice actually on here, and once in person, features, and Seth also a couple of times. We have a Zoom audience and we have a YouTube audience. And I invite the YouTube audience to maybe send some, put some messages on the chat, and we can have some questions from the Zoom audience in a moment. But maybe I can kick it off with a couple of questions. Maybe the first one about the internal state, and the second one about engaging with the external state. The first one, but maybe preface this by saying that back in 2006, I think it was, I published a book called Camouflage, which was about how we adapt and identify with the world. It was actually very parallel to what Andy Clark was doing. And we know each other now. We didn't know each other then. He was working from a neuroscientific point of view, and I was working from a primarily continental philosophy, psychoanalytic theory point of view. And it's kind of strange how parallel, but not necessarily connected, those two worlds are. Particularly the notion of homeostasis that you touched upon. I was a colleague 12 years ago now at USC of Antonio Damasio, who of course talks about homeostasis. And I also came across homeostasis in the work of William Ashby. Curiously, Damasio didn't know about William Ashby's work on homeostasis. Never mind. It was, when I was listening to Damasio, it really resonated with the ideas that I've been working on, coming out of Freud largely for the world of psychoanalysis. And I mentioned this to him, and he commented that really Freud had been a huge inspiration. By contrast, when I was talking to Anil Seth, who was someone I really admire as well, but very different, obviously, I mentioned psychoanalysis, and particularly the work of Zizek on the role of fantasy, and he was very dismissive about psychoanalysis. And I'm just wondering, how do you see any parallels, or do you find it productive in some way? And would you buy into Damasio's thinking about the logic of homeostasis and how it might come out of Freud, maybe?
Yeah, that's a great question, where you're linking at least three massive disciplines together. Some of them want to be linked and some of them don't. So yeah, I think there's certainly the aspects of Damasio's work, say for example, somatic marker hypothesis and its resonance with sort of Jamesian notions of selfhood based upon, say, James Lang theories of emotion. I think they actually, I'm surprised that Anil was, perhaps he wasn't dismissive of Damasio, he was dismissive of the other, but that would certainly be very close to Anil Seth's commitment and focus on embodiment, and in particular introception. So one of the most, we didn't talk about it in those numerical studies that I was illustrating, but a really important source of evidence for the lived world is our own body. And that comes along with the implication that perhaps a certain hypothesis, a certain fantasy apt for explaining my sensed world is that I am a body, I am that self. And, and then you can, sort of, as I'm sure you've done, have arguments about minimal selfhood of the kind that Anil would insist really requires being a beast or being a beast machine. And from the point of view of inferences about self, which I would also, which I would take as emotional inference. So it's not, it is almost banal to say, yes, I've got a representation and a hypothesis, and I am a self. That, you have to, if you like, motivate why that would be useful, why that would make you, why that would be part of maximizing the evidence for your generative models. And it would be so if you can infer you are a self in this context, in this state of mind or that state of mind or emotional state of mind. I am frightened, I am happy, I am embarrassed, all of this, and perhaps then one could go to Paxepian sort of ontology of emotions. So from that point of view, I think, at which point then you get back to this circular causality that I think is inherent in James Lange formulations of emotion, and I think underwrites the somatic marker hypothesis that Damasio was trying to emphasize, that emotions have to be evidenced in some way, and you have to make sense of the evidence for that, and those key cornerstones of evidence are the somatic markers of the kind of the state, my emotional state at this point in time. So I think there's a really dense set of connections there. When it comes to analysis, though, then I think you're now talking. Well, and my apologies. Homeostasis is clearly sort of the physiological reading of this kind of this kind of construct. How does that relate to Freudian ideas? I suspect very closely. So I'll answer that first by just noting that Freud, of course, was originally a neurologist, a neurobiologist studying neurons. He was growing up at the same time as Helmholtz was talking about neuronal energy and psychic energies and Helmholtzian physical free energies. So I'm pretty sure that had Freud had the opportunity with Helmholtz to go and speak to, say, somebody like Richard Feynman a few years, all of these free energies would be exactly the same. The Freudian free energy, Helmholtz's neuronal or psychic energy would all be the same thing. It would be basically, have the mathematical form that Feynman brought to the table. So it would be very unsurprising to find that some of the tenets of Freudian work were not exactly consistent with that of Helmholtz, and subsequently the refinements we've seen in the 20th century and now in the 21st century, with work by people like Andy Clark and Neil Seth and Damasio and the like, and yourself. When it comes to the psychoanalytic interpretation itself, I have to say there is a whole other community which doesn't really talk to Neil Seth or Antonio Damasio, but it is very invested in sense making and philosophical issues that I suspect would engage you. And I'm thinking here of the neuropsychoanalysis movement and of people like Mark Soames. So Mark Soames, a bit like Neil, would take a very sort of pragmatic view of the importance of having the substrate of computation and sense making and being in the equation, but from the point of view of a neuropsychologist, looking at the consequences of losing bits of the brain, either pharmacologically or in terms of lesions. So that would be sort of the neuropsychology part of the analysis. But he's also the world's expert on Freud, having just celebrated the second, or the RSE, the Revised Standard Edition, after 30 years of hard work. He now knows Freud inside out. So he, I would go and ask Mark Soames that question. There are some fascinating, I think, links. I have to say that they largely boil down to a particular aspect of this active engagement and homeostasis, which is not so much about the mechanics and the content, but the attention paid to various sources of evidence. And if you're in psychology, this could be read as attentional gain. If you're in engineering, it would be setting the Kalman gain. And if you're Mark Soames, this would be a measure of felt uncertainty, and it would be the genesis of actual feelings and sentience in and of itself. So that's quite an interesting, if you like, what emerges from the functional form of the mathematical descriptions of these processes, these belief updating processes in this particular context, actually highlights a very special aspect of this view of sort of active sense making. So, have you had Mark on this series before?
No, not yet. No, but it sounds like it's a great person you should get on. Yes, yeah.
Yeah, no, I think you'd really enjoy speaking to him. So even to the extent I will defer any more answers about the analytic and Freudian. So you need to speak, I think, to Robin Carhart Harris and Mark Soames. I think if you get those two chatting, not together, but if you could chat to them both, I think you get a very rounded picture on how one can bring Freudian ideas center stage in these kinds of in these 21st century physics-based kinds of accounts.
Maybe I can ask my second question. Then there's Sonia Diego who's got a question here. But my second question is really many of the audience here are designers, and I guess one of the key things is what is the impact of design on us in some senses, and the question there would be how this internal state is in some ways affected by the question of design itself. And in some senses, maybe to give you one example, I'm always struck by how in architecture, and I'm trained as an architect, you'll be in, let's say that the kind of the sublime mountains of Switzerland, really jagged mountains, and there would be this minimalist building that's a very famous baths by Peter Zunter that's absolutely exquisite, but it's completely contrasted to the environment, and it's almost like it's a dialectical foil to balance out the kind of excess or the irrationality of this thing with this pure. And also in the Netherlands, which is typically quite flat as a country, we have some quite provocative architects who are doing complex forms, beautifully curved complex forms, UN Studio and a few others. And so it's almost like there's a kind of balance. You're trying to use that external world as a kind of that homeostasis could include the external world. How does that resonate with you?
I think it resonates in three ways. First of all, that notion of design, I think you could, at least semantically, if not in many ways, connect to Andy Clark's designer environment, and just generalizing that notion, the whole notion of niche construction. Particularly in terms of architecture, I think this is very, very prescient. The architects and engineers are largely responsible for literally constructing our lived niche. That's important because, of course, as soon as you now create the causes of sensations yourself, there now becomes either a vicious or really virtuous circle of causality, and then you get into the game of thinking about, well, if you've got a lot of these active inference agents populating the same environment, that they are all co-constructing, how then does that work? And then you get into really interesting issues about communication and shared narratives, deontic cues, and the emergence of certain cues that have a semiotics or affordance that are shared between the denizens that are co-constructing their own world or their own niche. So I think that's a really important issue. The second important issue is the notion of affordances. So I could have told a lot of the story that I told today, but just using a Gibsonian notion of affordances. And in particular, so what are affordances in this setting? Well, they are just ways of evaluating the value of different active engagements with the world. Now, this engagement could be visually scanning the horizon for a beautiful building, or visually palpating a picture. Or it could be, do I go down that corridor or this corridor when exploring a church or a new piece of architecture? So it's all about, from the point of view of active inference, from the physics point of view, it's all about one aspect of that expected free energy. And I would submit it is all about the expected information gain, or the Bayesian surprise, the epistemic or the intrinsic value or the epistemic value of resolving uncertainty. So that underwrites curiosity. So you can read basically that expected free energy as just quantifying different aspects of affordance, and pragmatic affordance. Oh, I can take the weight off my legs, and I'm the kind of person, I'm getting old now, I'm the kind of person that sits on that chair. Or it could be this epistemic affordance, this information gain part of it, which I think is much more interesting. That means, well, if I did that, if I looked round that corner or went down that corridor or looked upwards, I would resolve some uncertainty. And I know that I would resolve some uncertainty, and that's very alluring. And I think that's a secret. That would be the secret source that the architect would be chasing. Designing architectures that draw the eye, and possibly even enable in a graceful way the not just the pragmatic affordances. Oh, I want to go and sit on that, but also the epistemic affordances. What's behind that? What does that mean? When things say about looking at pictures. So I think I think you could probably tell a very good story just about affordances from the point of view of design. And what you're trying to do is effectively have universal clickbait for every way that we can engage with the world, as opposed to just clicking on a mouse. So in an embodied sense, you are trying to leverage in a co-designed environment, or a designer environment, which we all design together. We're trying to leverage those deontic cues that provide that realize those epistemic affordances, or allow them to be realized through the choices we make, either whether, I repeat, visually palpating or literally walking through something. The final thing is a much more dull-minded, though. At the end of the day, so if I was a mouse, as opposed to a human admiring one of your buildings, what I'd be looking for is something that I can recognize very, very quickly and efficiently without worrying about planned, worrying about where to go or what to look at. And I'm basically going to be, if I had the choice, I would choose the kind of environment that I could predict very, very easily. What kinds of environment can I predict very, very easily? Well, those things that my visual apparatus has evolved to, which is basically edges. So I would build a world with lots of straight edges that can be detected very, very efficiently, simply because I have evolved to live in a world that, because of occlusion, produces edges. And thinking about minimalism, then minimalism has got two aspects to it. It's very simple. It's just about edges. But also it's a blank canvas that you can paint. So it also has this epistemic affordance to it. So to conclude, I think there are different levels. The designer could come in with certain constraints on what can be recognized. You don't want to present white noise, because there's no information content and there's nothing that can be recognized. But beyond that, it's recognizing that you can recognize something else if you did that. And I think that would be the sort of the second affordance-based approach.
Beautiful. What you were saying, kind of, I've yet to engage with Fei Li's notion of spatial intelligence, but I suspect there's a lot there for us to learn from. I don't know if you're aware of the work she's been doing, but I certainly Gibson is a central figure in a lot of our thinking in this group here. Okay, we have a question from Sonia de Jager, who's in Amsterdam, and doing a PhD on the philosophy of AI. And Sonia, would you like to ask a question?
Thank you. I'm in Rotterdam, but not too far. I used to live in Amsterdam before. Thank you very much, Karl. Nice to meet you. We've been chatting via email.
Yeah.
Yeah. Your last point about, thank you very much for the wonderful presentation. Your last point about edges actually is, this is the question that I want to ask is a nice follow-up, I think, from that. I've been thinking a lot about symmetry because I actually will be giving at the Active Inference Institute a presentation next week with Shanna and Daniel about symmetry. And the question is, it's very general, it's an annoying philosophical question. So seeing that we are structures, interested in structure, what's your feeling about, are we actually latching onto patterns out there, or are we simply in the business of producing them? I mean, I don't think this has a possible answer, but if you could speculate about our implication in patterns, our production and perception of them.
Well, I think the answer is both. Again, I think it's an instance of this circular causality that we are going to build environments that afford the right sensoriums that can be easily predicted, so that we are basically trying to aspire to a perceptual homeostasis, literally some peace of mind and some peace and quiet, which will never be attained given the capricious world that we are in. But that would be the simple, a simple description of the imperative behind this physics view of active inference. So what would that look like? Well, it would look as if you were building generative processes in the world that were providing sensory evidence that would support the models with the greatest evidence. Now, I express that in a long-winded way because there's a really interesting application of this decomposition of the log evidence into accuracy and complexity. So if you remember, one of the ways of decomposing and thinking about or interpreting the evidence lower bound in machine learning, or the variational free energy in active inference, or the free energy principle, and more generally just the log marginal likelihood or the log evidence for your models of the world, is into accuracy and complexity. So what does that mean? Well, it means that good models and by definition, the kind of sensory content that those good models have to explain have to be as simple as possible. To a mathematician, what is simplicity? It's finding symmetries. So symmetries in maths just means invariances, which means that you can reduce the degrees of freedom in an optimal way, so that the simpler explanation, the minimally complex explanation, is that which has the smallest degrees of freedom. From the point of view of inference, it basically means that I can build prior beliefs about my world, which I basically don't have to augment with or move away from when bringing those prior beliefs to the table to explain this particular sensory input. So if something is symmetrical, that means I can, for example, your face, I can reduce by a half the degrees of freedom needed just to list all the attributes that I would need to create a portrait of your face. So this minimizes the complexity enormously, and that in turn maximizes under accuracy constraints. It maximizes the model evidence. This is just the measure of existence or the goodness of a model. I mean that literally, in the sense, if you deploy this mechanics in evolutionary theory, the free energy bound or the log marginal likelihood is literally the likelihood I will find you as a phenotype, as a generative model of this eco niche in a population. It's just a probability that you exist. So and if that probability is inversely proportional to the complexity, you can see immediately why it is quite natural that we evolve to to be as simple as possible and as symmetric and as invariant as possible. And this has many readings, and in fact, readings that you will see in other fields. So, for example, people like Jürgen Schmidhuber, the inventor of long short-term memory, for example, and one of the I was going to say unspoken heroes, but he's actually quite loud. He's heroes of artificial intelligence. He'll always talk about the complexity minimization, and that story inherits from a view of intelligent sense making in terms of compression. So another instance of this can be traced right back to the notion of Kolmogorov complexity. That you can take then in terms through Kolmogorov induction through to universal computation. Basically saying the intelligent way to communicate or to summarize or to represent things is with the smallest degrees of freedom or the minimum message length or the minimum. It's all the same, I think, basic principle, sort of minimizing the complexity. I should also say, if you're a philosopher in this area, then you'll be also entertained by this kind of idea emerging in very different disciplines. So this is also James's maximum entropy principle. So having the greatest uncertainty that explains your measurement means you're not committing to a very detailed, very high degree of freedom explanation, which is, of course, Occam's principle. So I think all of these are fundamental aspects of the way that we not only perceive our world, but actually exist within our co-constructed world. Symmetry read as invariance.
Thank you very much. Yeah, you basically went through a lot of the things that I will be talking about for sure. So that's fantastic. Thank you. Yeah, one thing for me, like just to final small point, if it's possible. The idea of invariance under transformation is quite interesting because at least phenomenally or in the construction of kind of ever more complex structures, because we're interested in just, exploring and creating novelty. There is kind of an oxymoron there, right? Because there is, at least let's just take the phenomenal sort of invariance under transformation. There is something that needs to be tracked, which means that, well, there's certainly transformation, right? Like the fact that something is being transformed, like the symmetry of a face means that one has to assess the degree to which there is change or not between those two things. So that's the sort of
well, no, actually, that's a very good point, which I should have just mentioned as well. Yeah, that those kinds of invariance and transformation speaks immediately to the factorization into sort of what versus where, and that itself again is at the heart of physics in terms of mean field approximations and being able to sort of carve nature at its joints in the right kind of way. So yeah, that may be another aspect of this sort of symmetry as an invariance, but now a nuanced form in the sense that you can actually carve it into two kinds of invariances, one of whatness and one awareness, and yeah, absolutely.
No, it's super interesting to think about energy symmetries and sort of perhaps the sort of phenomenal symmetries, the smoking gun of all these lower level symmetries that we observe. It's yeah. Thank you. That's yeah. One.
Oh, we have a bunch of questions, very popular bit. I take them in strict order which they've been asked. So just to first of all, Dimitri has a question, followed by Mikhail, followed by Gabrielle and Alberto. So maybe, and then further down, yeah, well, we'll pause there. Dimitri, do you want to ask your question quickly?
Yes, Nel, thank you so much. And thank you, Karl, so much for the amazing lecture. I'm glad to ask one question. It's a little bit related to the idea of the perception recognition in the generative AI, especially recognition. So there is a prompting like in AI, and I was like bumped into some kind of prompt, which is called, if you imagine in one go, ultra-modern villa in a recomposed from the antique ruins, and these ruins reassembles into the futuristic composition, and this information goes in one go. So like for us to do it, we have to reverse the logic, and we understand it while we get in like entire sentence. And for the machine learning, there is three layers of the like logic happening. One is the decay structures of the of the antique elements with like broken cannulas and like capitals. Second layer is the recomposition. So maybe like one capital put it on top of another one, but it has to be put in a way so that it's still creating some kind of futuristic deconstructivism thing. So, and the cracks, like the another like point, going to be also bypassing with this thing. Of course, there is a possible to use some kind of informational masks, but what would be the logic or epistemology of the information? Because in one go, we suggesting three streams of the information. Thank you so much.
Right. That's a fascinating example. I'm not sure that I can answer your question because I'm not absolutely sure I understand the nature of the question in terms of goal. But I think what that example brings to the fore is a really interesting issue, which is having a generative model that has dynamics in it and the role of time. So in many respects, I could read your example. If I had a generative model that allowed things to fall down and to decay, say of a new building that was then became decrepit or lost its structure and the materials changed. I could have a good generative model of that process of decay, for example. And then if I had that model, I could run it backwards in time and thereby build it up again. These models are really important because they beg the question, well, is there a difference between running it forward and running it in backwards in time? So having the dissembling and having the assembling. And yes. The answer is, of course, absolutely yes. But that's not necessarily true for all kinds of processes. So you won't find reversible processes that you'll find in 20th century physics, equilibrium physics, don't have that property. They don't break detailed balance. Whereas the kind of real world process you're talking about and would like to model or simulate or understand breaks detailed balance and has this arrow of time baked into it, in the sense that running it forwards and running it backwards are not the same thing. So one can imagine a simpler example: stirring a cup of coffee in one direction. You would know whether you're going forwards or backwards if you started in the right way. Whereas if there was no indicator, there's no shaped cream on the surface of the cup of coffee, you wouldn't really know whether you're going forwards or backwards. The interesting thing here, just to connect it back to Helmholtz, is that the breaking of the detailed balance that gives you these irreversible processes that could be reversed in your head or in image reconstruction depend upon that solenoidal part of the Helmholtz decomposition. So that's the role of Q, and I think that makes everything much more real world like, and I would also argue lifelike. So another manifestation of this breaking of detailed balance and the fact that going forward in time matters in relation to going backwards in time is the notion, when you have that solenoidal or that kind of dynamics in the context of an attracting set, what you're saying immediately is that this system has to have oscillations. It has to have a periodicity. So that means you can't have any life without oscillations, whether they're oscillations in my head or life cycles from the point of view of reproduction or evolution or phases of development. Wherever you look, you have to have oscillations. So that would be, if you like, another manifestation of the importance of having or living in a world that breaks detailed balance, where you're in these non-equilibrium steady states, but also having to model that. And I presume in your world you actually have to simulate this as well, and do these things. One final point. I wasn't quite sure the example you were talking about, so forgive me if I misunderstood, but I got the impression that you were breaking a building down, then building it back up again, and it was different and modern. There's a really interesting connection there with forward and time reversal protocols in physics.
Well, here I was like referencing to the Simondon idea of the ruins, and but the ruins which are reminiscent with ideas of the objects, which is cannulars, and the thing which is keeping the memory from the past. While if they are recomposed in a new shape, they are like can create the compositions any other like stones or like modern kind of like aspects. That was like the exercise I was trying to do, and for me, it's amazing answer. Thank you so much for that. I was like, for me, this. I just wanted to share this real quick that this moment when information goes into the meaning remains the mystery for me, like for us, because it seems to be last instance of the object somehow, because the meaning somehow already a part of us, while the information is a part of the externality. And I was like thinking about this idea of the coding through the prompt, which is somehow trying to like delivering the meaning like with the predictions. So this is kind of falling to the information realm. So the image becoming the informational part. That is the case. Thank you.
Yeah, thank you. That's a really important point. Yeah. These beliefs that I was talking about are beliefs about something. It's information about something. It's not, just the information content of the neural dynamics. It's what it means for, either this stone as it was 100 years ago, or this stone now. And if you have a model of how stones change, it can have all sorts of meanings by rolling forwards and backwards in time. Absolutely.
Thank you so much.
So we have a question from Demetrius is an architect in Shanghai about to start a PhD in Russia, and we now have Michael, who is an artist, an art theorist based in Berlin, but doing a PhD in Hong Kong. Michael.
Yes, thank you, Neil. Thank you so much, Karl, for this really amazing and super interesting lecture. I will need definitely a second round here. There are for me there are so many questions that come to mind, but one I meant to address here, which I think is a very profound topic, is concerning the boundary. I mean, the boundary sort of in all its complexity. And if I can briefly quote here from a paper, a great, amazing paper from 2017, from you and your co-authors, the Markov Blankets of Life, where you write that the boundaries of such systems need not be coextensive with the biophysical boundaries of a living organism. And I think this is extremely interesting, as you've already pointed out, in terms of niche construction, because, of course, I think architecture, in a sense, is all about boundaries, but certainly not just physical boundaries, but all kinds of relational boundaries. Or maybe we could say interfaces, or have other sort of related concepts concerning boundaries. But there is, to get to the question, there is a very interesting recent MLST episode, I think it's a year old or so, with you on anactivism, and of course there is this paper laying down a forking path from 2022, where the authors claim certain incompatibilities between activism and the FAP. And if I can briefly quote again, they're saying, we argue that these ideas, meaning their ideas, are incompatible with the time invariance of non-equilibrium steady states assumed by the FEP. So my question here, if albeit a little vague, is how do we think about, let's say, boundaries from your perspective and invariance? What is, because of course there, yeah, I suppose this is for me is something I've been struggling with for a while, and maybe there is no certain answer to this, but the idea of the boundary and the invariance, how would you approach this? Thank you, Karl.
Yeah, you make some excellent points there. Just very quickly, just to rehearse some of the key points. So you can certainly read the Markov blanket as an interface. If you're a systems theorist, it would just be the collection of inputs and outputs to a system. So before you start any system analysis, you have to say this system has this inputs and this outputs. They're just the active and sensory states. It's just the interface with the thing that's not the system. So I think that, you know, it's important to say that there's nothing magical about the Markov blanket. It's just that it is defined mathematically in terms of dynamics and causal influences that can be related to physics. The second thing to say is that you're absolutely right. These blankets are not coextensive, can be or cannot be may not be coextensive with blankets at different scales. And there is no unique Markov blanket, so that I could become, depending upon the scale of analysis, the Markov blanket that constitutes me could be physically embodied in my surface, or it could be within my physically embodied blanket, and it could be divided into cardiac systems and central nervous systems, and everything that has a semantic or a label would be equipped with a blanket, right down to sort of molecules in particular cells in parts of my brain. So we have this notion of a multitude of Markov blankets nested within each other. And once one has that notion, it becomes obvious that in order for one blanket at a small scale to exist, it requires the existence of the blanket at the higher scale. So, for example, one of my heart cells requires the existence of a Markov blanket that defines my heart. In the absence of a heart, I can't have a heart cell. That heart requires a Markov blanket that defines me. I depend upon my familial ecosystem and my my geopolitical ecosystem, the population of which that itself depends upon a Markov blanket around Gaia, around Earth, and so on and so forth. So you've now got this multiple dependency on Markov blankets at different scales. The key thing here, which is now going to be the answer to your final question, is that as you move up scales, in accord with the application of the apparatus of the renormalization group, your time scale increases, which means that the Markov blanket that provides the context in which a smaller set of Markov blankets exist for a certain period of time always has to last longer, or will always last longer than the Markov blankets at the lower scale. And the Markov blanket at the higher scale inherits from and is an average of the more quickly fluctuating Markov blankets at the lower scale. So what you have now is a hierarchy of scales where things that are encompassing at a very, very high coarse grain scale are changing very, very, very slowly, so that they provide a not time invariance. We're not talking about time equals infinity, but from the point of view of things that live in this context, it looks like forever, longer than my lifetime. Whether I'm a molecule or a cell or an organ or an organelle or a phenotype or a population, as soon as I look to the scale above, it looks as though that's lasting forever from my point of view, because I'm going to die. I'm going to go through all my life cycles before as an individual before I get there. So I think that would be if you like, the dissolution of the worries about ergodicity and time invariance. There is no time invariance other than at the temporal scale at which you are talking. Whilst you are talking, you're fully acknowledging that there are contextual scales which have a greater time invariance, but also at a finer scale, there is no time invariance. So we're just talking about the attracting set existing over an appropriate time, appropriate for the scale of analysis. So and it's up to you, what you pick. I mean, some people might pick a few minutes if they're looking at sort of nerve cells in cultures that may only survive for a few minutes in their form. But if you're a psychologist examining a person, the timescale could be years. So you have to pick your scale at which to apply the principle. And I'm just trying to relate that to art. Yeah, perhaps it can be, but yeah, perhaps there is self-similarity. So along with this notion of the renormalization group and another kind of symmetry in terms of the dynamics being conserved as you move from scale to scale, as the scales increase, I'm sure you find that you must find that in art. There are certain scales that you can focus on. And yet there is something conserved across scales, even though they last for either shorter periods of time or for shorter distances on some canvas.
Thank you, Karl. Very interesting. Thank you.
We have a question from Gabrielle. I suspect it's the same Gabrielle that Sonia mentioned. Gabrielle, I'm not quite sure where you are. Would you like to ask a question? Yeah.
Hello. First of all, thank you for your fascinating presentation. I'd like to explore deeper into the concept of expected free energy that you introduced, like particularly in relation to reinforcement learning. So in your formulation, you described expected free energy as having components of intrinsic and extrinsic value, where the intrinsic value, if I understood correctly, relates to information gain or a reduction of uncertainty, while the extrinsic value connects to expected utility or reward. And this framework reminds me of the exploitation dilemma in reinforcement learning, where like agents must balance between gathering new information about their environment while exploiting known rewarding actions. This question is I think it has to do with how we as architects also engage in that same balance of exploitation and exploration.
Yeah, that's an astute question, and you're absolutely right. So those two, that way of expressing the expected free energy in terms of intrinsic and extrinsic is exactly the imperatives for exploration, intrinsic, and exploitation, extrinsic, of the kind that you would find in reinforcement learning. The use of the word intrinsic value also is a nod to intrinsic motivation in robotics. So there's a whole field of robotics where you're trying to understand exploratory behavior, particularly actually behavior that reveals what the robot can control and what it can't control. So it's a very important kind of self-exploration, and that can't be rewarded in terms of conventional reinforcement learning, because the degree to which you learn something depends upon what you already know or believe. So it's changing all the time. So it's not something you can sort of reward. It's very intrinsic to to yourself, which is one reason why it's called intrinsic motivation or intrinsic value. So you're absolutely right. The whole point of, if you like, offering expected free energy as an explanation for motivated or sentient behavior is that it dissolves the exploration exploitation dilemma. How does it do that? Well, it basically puts the information gain and the utilitarian or pragmatic or reinforcement learning like gain in the same units of measurement. And once you've done that, then you can combine them on an equal footing. So there is no dilemma now. You can just put them together. Sometimes the epistemic part, the intrinsic part, supervenes, and sometimes it's the utilitarian extrinsic value that supervenes. You don't have to choose how to balance. You just add them together. And you get the most likely action. So what tends to happen when you deploy this kind of mechanics in simulations is that when you enter an unfamiliar environment, every move you make has a very, very high epistemic value or intrinsic value that dwarfs any pragmatic value in terms of exposure or some particularly rewarded attribute of the sensory input. But as time goes on, you learn about your environment, and the epistemic value of every action starts to fall. And as soon as it falls below the threshold set by the pragmatic value or the extrinsic value, you suddenly switch to exploitative behavior. So the behavior you get is, I'm going to be exploratory until all the intrinsic value or the epistemic affordance has been exhausted, because I now know this environment, I know this painting, I know this building, and then you just become exploitative in the sense, I'm just going to do the kind of thing I normally do, which is the expected utility part. I'm just going to act in a way that brings about my characteristic states. I'm relaxing in a, I'm doing this in this particular context. But you can only do that if you write down reward as a log probability. So to put exploration, exploratory, and exploitative drives into the, or put it another way, to interpret the free energy principle in terms of exploration and exploitation, you have to transform a reward function into a potential function, which is a log probability. So now you write down your reward as the logarithm of a probability that this will happen to me. So if I have a prior preference or belief that I am the kind of thing that gets a reward, then the log probability of this outcome becomes very, very high. And that's the intrinsic value. So you can reproduce reinforcement learning in active inference or with expected free energy, provided you can write down the reward as a probability distribution over all the outcomes that you might that you could encounter. You don't have to write it down precisely. You don't have to work out the precise range of many different outcomes, which are completely relevant. But there'll be some important outcomes, such as if you're doing, say, homeostasis, there will be the temperature if you're in the physiology. So there, I have prior preferences that my temperature is within a certain range, and provided I am, I'm in that range, I can then use, I can choose those actions that will be exploitative. But if my temperature exceeds those with some action, then that pragmatic part, the extrinsic value, kicks in and will then dwarf the epistemic part. Does that help? Is that the kind of thing you had in mind?
That's very interesting. I'm definitely going to have to revisit this video as soon as it is on YouTube. Thank you very much.
It'll be on YouTube as soon as it's finished. It goes directly uploaded onto it. We have so I'm not quite sure where Gabriel is, but where are you, Gabriel? Okay, well, we have Alberto, who is originally from Cuba and currently in Miami doing a doctoral design at Florida International University. Alberto, would you like to ask your question?
Hi, Karl. Thank you very much for a fantastic presentation. You brought me back to who I was before as a nuclear physicist that I'm not doing any longer. But I have two questions for you. The first one is about predictive models and creativity. And my question is, can the brain's predictive model framework, as described in the free energy principle, explain how humans generate novel ideas or creative thoughts that don't seem to have a prior sensory input?
Yeah, that's an excellent question. I think, again, I'm mindful of time. Everybody must be getting quite exhausted by now, but that was a really important question. But I think could be answered at two levels. The first one actually speaks to the past discussion about exploration and the expected information gain, or the epistemic affordance part of the expected free energy. that also applies not just to states of the world, what's behind that corner, but also the parameters of your generative model. Can I open this door? So that would normally be read not as salience or the epistemic affordance of looking behind that door. It's more, what will I learn? Can I open this door? Is it an openable door? And that's usually formally discussed in terms of novelty. So you can either read the epistemic, the information gain over states of the world that you're trying to infer as the imperative for salience, where salience now is effectively an affordance. Or you can apply it to the parameters of a generative model, so the connection strengths in an artificial neural network. And then you can say, basically, this provides an allure because it is novel. So there is novelty seeking built into the right way of minimizing expected surprise. I mean, heuristically, you can see how that works. Obviously, if I'm the kind of thing that indulges in novelty under the constraint, I'm not going to enter very costly outcomes because of that pragmatic part. So I'm still going to be safe and alive and the right temperature. But given that constraint, I'm going to do those things where I learn the most about my lived world. Then I'm going to be, on average, less surprised over a period of time because I'm curious. So I think that novelty seeking is an important aspect of the kind of base optimal behavior that inherits from this non-teleological physics treatment. I think, though, the better answer to your question is implicit in your question: can you create new ideas? Can you do something that's never been done before? I think that that is the essence of the creative aspect of the novelty of things that have been created, and that speaks to a really interesting question about the scale at which you are looking for surprise or free energy minimizing processes, or what some people have possibly called self-evidencing. So if you remember, the surprise is a negative of model evidence. So to self-organize under these imperatives is to self-evidence, to gather evidence for my model of the world. That evidence can pertain not just to the states, which we've spoken about in terms of salience, or the parameters of the model, which we've spoken about in terms of novelty and learning, but also to the very structure of the model itself. And this takes you into the world not of inference or learning, but Bayesian model selection, selecting the right model.
That's good.
That is apt for this. At this point, then you need to have the ability to create new models, things that have never been there before. So, I imagine that if you are building neural networks, you're going to try adding an eighth layer or factorizing it in some way that no one has ever done before, just as a hypothesis, because this structure now might provide a better account of my lived world, bearing in mind that I'm also building my world. So remember that we're always acting and building, constructing the world. So it's my world I'm building, but I still have to explain it because there are bits of it I can't control and are controlled by other things. So by building a new model or exploring, evaluating a new model, you can now select whether your new model is better or worse than your old model simply by gathering up the evidence, the log evidence, and adding it or taking a pathological of the free energy. So in statistics, this is Bayesian model selection. It's the bread and butter of much of the scientific process. In ethology, well, actually, in theoretical biology, you can also read this as natural selection, which sort of means that evolution is quite creative because it manages to create new structures and phenotypes every generation and tries these out as hypotheses and then selects the ones that have the greatest marginal likelihood or adaptive fitness in the usual way. But if you can do that in your head, then you would be a creative person.
Thank you. The second one is very brief. It's about I am doing.
I think, sorry, I think we got to be very careful about our time here.
Okay.
I'm concerned about Karl. I can see the light fading behind Karl. And we should try and wrap things up in a few minutes. I'm just wondering, Karl, could you take one more question?
Yes, of course.
Just one more. Okay, I just want to pick out one out of there's a whole list of ones there, but there's one from, I think, a very good one from Vashkor, who is in Dhaka and Bangladesh. We are spanning the world today, and I'm going to read it out because normally his question it's noisy in the background. The question is in the chat, actually, but anyway, how crucial is physical embodiment to achieving AGI? Could a disembodied AGI, for example, purely digital or virtual, react in the same reach the same level of sentience and intelligence as an embodied one? That's a beautiful question. How crucial is physical embodiment to achieving AGI? Could a disembodied AGI reach the same level of sentience and intelligence as an embodied one? Yeah.
Right. Yes. So I could spend another hour talking about that question. I'm not going to answer that, but I'm going to give you the answers which some of my friends would give you. And the answer is no, you have to be embodied. You can't have authentic agency without being an agent, and you can't be an agent unless you have a way of intervening on the world. And you can't intervene on the world unless you have a body. Obviously, the definition of the body now becomes a key question in and of itself. But if I read body in the general sense that I have a way of articulating interventions on the world that matter in a way that the world delivers the responses to those interventions, then yes, you have to have a body to be an agent. That doesn't mean to say you can't be an intelligent perceiver and data assimilator, but that's not agency. And I would not read when people talk about AGI, I always assume they actually mean intelligence that acts or at least can recommend. So there's an implicit aspect of agency in AGI, and agency, from my point of view, it requires generative models that include the consequences of action so that you can evaluate that expected free energy. So that was exactly the bright line that I was talking about between the single cell and the mouse. If you're associating generalized artificial intelligence or artificial generalized intelligence with things that can that have agency in the sense that they plan, then they have to have a model of the consequences of their action. And to act, you have to be able to, you have to have a body with which to act. There is another view of that answer, which rests upon the notion that Geoffrey Hinton again brought to the table, which is mortal computation. So you might, if you go on Wikipedia or at least Google mortal computation, I think it's a nice concept, and it sort of brings to the table two notions of mortality in software. When your question was read out, I was just thinking, oh, he's talking about immortal software. So immortal software is software that lasts forever, and you can run it on any hardware or any machine. And therefore, because it can be run anywhere, it's immortal. And that's to be distinguished between mortal software, where the substrate of the computation actually matters. It is part of the software or the computation, such as your brain and my brain. So if the hardware, the substrate dies, then so does the software. So much of the knowledge is actually in the architecture. For example, connection weights in my brain, as opposed to connection weights on a von Neumann architecture that can be read from and written from memory. So mortal computation, I think, is probably going to be a requisite of artificial general intelligence for two reasons. One, that's the only way that it can be realized in a sustainable way from the point of view of the energetics or the thermodynamics of inference and prediction. But probably more importantly, and this is an argument brought to the table by one of my friends, Alexander, that if you are immortal, there's no reason to avoid dying, and therefore there's no reason to act in a way to underwrite your existence. And the whole point of active inference and the free energy principle is to describe those things that actively maintain their homeostasis. So if you are immortal, you don't need to have a homeostasis because you can't die. So there are no constraints you have to satisfy. I mean, this is a bit of a loose argument, but it does allow you to think about self-organization and intelligent behavior as basically eluding the constraints, basically those states that you cannot occupy and still remain the kind of thing that you are. Which is another way of looking at reinforcement learning. Or no, it's not. It's another way of looking at those prior preferences or that extrinsic value. It defines the outcomes that are not consistent or characteristic of you. So it tells you what to avoid. And of course, if you're immortal, there are no constraints you have to satisfy. And I don't think you could really call that intelligent behavior. So that would be my answer on behalf of lots of people, including Andy, in fact. So Andy and Paul Cizik and Giovanni Pizzulo and my friend Thomas Parr, we wrote this down in an article in TICS about sort of artificial general intelligence. But there are lots of people who would argue. Stephen Harnard has some very interesting arguments about embodiment and mortal computation. And you can also take these kinds of arguments and ask, is this an important drive to neuromorphic computation, for example? And is that a more sustainable way forward as opposed to large language models on von Neumann architectures? And many people would say, yes, it is. And it's important we make that move quickly.
Karl,
thank you, Professor.
We must let you go. Thank you so much. I can just see the light fading in Northumberland, but it's been a wonderful session and so informative, so rich, and thank you for the generosity of your answers also to these questions. Something's very special. It'll be uploaded automatically onto our YouTube channel, and it'll be available for everyone around the world. This was very, very special. I'll just mention briefly before we wrap up that we do have a session, a delayed session. BLAISE ARCAS was rescheduled. It's on next Friday, and it's going to be about AGI, probably taking a very different viewpoint. But nonetheless, this is like the beauty of this forum. We can get a wide range of different approaches. Thank you, Karl. This was so special. And I've had some comments coming in. A colleague at MIT Media Lab was saying, what an amazing talk. You've got a lot of fans now. And maybe sometime in the distant future, we can invite you back. But this was beautiful, beautiful, beautiful. And thank you also to the team behind this to put this together. We have a team all over the world. Most of our posters are done by someone in Syria. We are literally spanning all over the world. Thank you, Michal, as well for and the whole team in Digital Futures. Karl, thank you. Amazing.
Thank you. It's been wonderful. Thank you for those gracious comments and the support of all your team. This has been a wonderful afternoon.
Thank you. Thank you.